Hello everyone, this is Deepashri. Welcome back to my channel. This is my second video. So in this I done part 2 introduction of real number. So in last video I done part 1 for introduction of real number. Okay. So now we will go with part 2 introduction of real number. Last class we discussed about Euclid's division lemma theorem. So now we learn what is the application of Euclid's division lemma. So let's see how it works. So it works to find HCF of two numbers. So here we took two numbers. Find HCF of 455 and 42. So just recall Euclid's division lemma. What is Euclid's division lemma? For any positive integer a and b, there exists a unique integer q and r such that a is equal to bq plus r. That is the equation we had. So here let's take a is equal to 455 and b is equal to 42. Why? To find HCF. So what is q? Q is quotient, and what is r? R is remainder. So to find quotient and remainder, you have to divide this a and b. So to find HCF, we have to divide till we get 0 remainder. So what we get, remainder should be equal to 0. Till that much division process should be continued. So now see how it is. So what is a? 455. Okay, now divide this. So you get 42 and here 455. So let's note that what is 42? 42 is b and 455 is equal to a. While you divide this, 42 tens 420. So what is the remainder here? 35 is the remainder. So now 10 is the quotient and 35 is the remainder you got. So we have by Euclid's division lemma a is equal to bq plus r. Now substitute here. What is a? 455. What is b? 42. And what is q? 10 plus r. Remainder is 35. So what we got here? B value 42. So now take it as a. So now 35 becomes b and take this number which you get here, that is 42. So take that b as what? A. Now find the quotient. So what is the quotient? 35 ones are 35. So what is the remainder here? 7 is the remainder. So this is quotient. 1 is the quotient and 7 is the remainder. Now write in the formula a is equal to bq plus r. What is a? 42. What is b? B is 35 into q is equal to 1 plus r. Remainder is 7. So you got 35. So now we have to divide 35 by 7. So you have to divide 35 by 7. So what is 7 now? 7 is b. 35 is equal to a. So 7, you know that 7 5 is 35. Therefore, the remainder you got 0. I told you have to divide till the remainder is equal to 0. So now 5 is quotient, 0 is a remainder. So now again write in form this. A is 35 and what is b here? 7. What is q? 5 plus r. R is what? 0. So here the last number is, the last value of b is what? 7. So you have to get the remainder 0 till this. You have to do the process After that, which one is the last value of B? That is 7. That is the answer. So 7 is the answer of what? 7 is the answer for HCF of 455 and 42. So therefore, write down, therefore HCF of 455 and 42 is what? 7. So this is theorem 1.2, fundamental theorem of arithmetic. This is very important theorem which will help in the next theorem or for the next problem. So this is very important theorem, that is fundamental theorem of arithmetic. Every composite number can be, say composite number can be uniquely expressed as a product of primes. So every composite number means what is composite number and what is prime. Once recall that, this I done in the introduction part 1. So you know that 2 is a composite number having more than 2 factors and prime number having only 2 factors. So to see here, if you consider 2, so it can be written as 2 1s are 2 and 1 2s are 2. So there is 2 factors. So if you consider 3, 3 1s are 3 and 1 3s are 3, only this much. So there is 2 factor. It also has 3 also has only 2 factor. 4 1s are 4, 1 4s are 4, 2 2s are 4. So this has 3 factor. 1 2 3 factor. 5 1s are 5, 1 5s are 5. So this has 2 factor. Again, if you consider 6 1s are 6, 1 6 are 6, 3 2s are 6, 2 3s are 6. So which has 4 factor. So composite number is, if it has more than 2 factor, then it is composite number. Which all have more than 2 factor? So this is 3 factor and 6 has 4 factor, more than 2 factor. These type of numbers are called what? Composite numbers. So 4, 6, then similarly 8, 10, 12 and so on, 9, even 9 also of what? These all are what? Composite number. So these composite number, and what is these are called? If there is a 2 factor for any number, then that is called prime numbers. So here they told composite number can be expressed as a product of primes. So what is prime? Here you can see prime composite number. So 4 is a composite number. Composite number can be written as 4 is equal to 2 into 2. What is 2? 2 is prime number. So it can be written as 4 can be written as 2 into 2, means these two are composite number. You can write prime composite number in the form of product of 2 prime numbers, or how many prime numbers. 6 can be written as 3 into 2. So this 3 and 2 is a prime number. Similarly 8 can be written as 2 into 2 into 2. So it is this composite number is a product of prime numbers. Let's take one example, 150. I will take 150. So if you take prime factorization of 150, so you get, it is 150 is divisible by 2. So 2 7s are 14, 1 remaining, 2 5s are 10. Again 75 is divisible in 3, 3 2s are 6, 1 remaining, 3 5s are 15. Then this is divisible by 5, 5 5s are 5 1s. So in this you can write 150 as 150 equal to how? 2 into 3 into 5 into 5. 2 into 3 into 5 into 5. Similarly, you can also divide this by taking first 3 or 5. So you can divide by 150 by 3 also. So 3 how much are? 350s are, again this is 5, take 5. So 10s are, again you can take 5, 2s are. So then you take 2 1s are. So again you can write 150 as how? 3 5 into 5 into 2. Now again you can write 150 again also. You can divide starting from 5. So you get 5 threes are, that is again you can take 3 tens are, and you can take 5 twos are, then 2 ones are. So here you can write again 150 is equal to 5 into 3 into 5 into 2. So here you can see that 150 can be written as 2 into 3 into 5 into 5, 3 into 5 into 5 into 2, 5 into 3 into 5 into 2. So here in each case, the prime factorization of composite number can be written in different form. Like this written in 2 into 3 into 5 into 5. If you see this case, 3 into 5 into 5 into 2. Here 5 into 3 into 5 to 5 into 2. But in which these prime factor occur in the different order, isn't it? It is in the different order. So that is for the order in which these prime factor occur in different order, but the prime factor remains same. Is it prime factor? What is the prime factor here? 2, 3, 5. 2, 3, 5. Here 5, 5 is here 3, 5, 5, 2, which all are primes are same. 2, 2, 3, 3. 5 times 2 times 5 repeated, 2 times 5 repeated. If you want to see here 5, 3, 5, 2, which is repeated same. 5 2 times, 3 1 time, 2 1 time. So this what here prime factor remains same, but the order will variation. There is a variation. So there is some standard form to write in order, to set in order. There is one standard form. So we have to write in ascending order. What is the ascending order? So we have 3 into 5 into 2, 5 into 2, 5 into 3 into 5 into 2, 2 into 3 into 5 into 5. So what is ascending order? Ascending order means in increasing order. You have to write, first you should note the least prime number. So in this, which one is the least prime number? 2 is the least prime number. So first you should write 2, then you should write 3, then you have to write 5 and 5. So this is the way to write in the to set it in a standard form. So this is what fundamental theorem of arithmetic. Now let's see how to find the prime factorization of any composite number. So there is you know that by fundamental theorem of arithmetic, composite number can be written as a product of a prime number. So now let us see how to find prime factorization. I will take one example, 32,760. So now let's see the prime factorization of 32,760. So here I told there is a standard form. To set it in a standard form, we have to write in a ascending order. So which are the primes from starting 2, 3, 5, 7, 11, 13 and so on. These all are what? Prime numbers. So first we should take 2. Now we have to check whether it is divisible by 2. Yeah, it is, the last number is 0, the last digit is 0, so it is divisible by 2. So 3 is not divisible, so 2 ones are 2, 1 remaining. So here 1 remaining. 2 how much are 12? 6 are 12. So 7 is not divisible, so 2 3s are 6, 1 remaining, 2 8s are 16, 0 right as it is. Again it is divisible by 2. So you have to divide first by 2. If it is not divisible by 2, then you would have to take by 3. So now again 0 is the last digit, so it is divisible by 2. 2 8s are 16, 2 1s are 2, 1 remaining, 2 9s are 18, 0. Again you got 0, it is divisible by 2. 2 4s are 8. So 1 is not divisible by 2, so take 0 and take 19. So 2 9s are 18, 1 carry, 2 5s are 10. Now you got 5. So it is not divisible by 2. So the next prime number is 3. But you know, whether you know where you don't know whether 4095 is divisible by 3 or not. So let us check. So you have to add all the digit in this number. So which are the digit? 4095. So add 4 plus 0 plus 9 plus 5. Why? To check whether it is divisible by 3. So while adding you get 4 plus 0 plus 9 plus 5 is how much? 18. So now you have to check whether 18 is divisible by 3. Yes, 3 6 are 18. So this is divisible by 3. Therefore this whole number is divisible by 3. Therefore you can divide by 3. So 3 ones are 3, 1 carry, 3 threes are 9. So 1 carry again, this you get 10, right? So 19 is not divisible. So 3 6 are 18, 1 carry, 3 5s are 15. So again you have to check whether it is divisible by 3. So I have to add all the digits. 1 plus 3 plus 6 plus 5, you get 11 plus 3, 14, 15. So 15, yeah, 3 5s are 15. So 15 is divisible in 3. Therefore you can take 3. So 3 4s are 12, 1 carry, 3 5s are 15, 1 carry, 3 5s are 15. Now again you have to check 455 is divisible by 3. 4 plus 5 plus 5, which is equal to 9 plus 5, that gives 14. So this is not divisible by 3. Therefore 455 is not divisible by 3. So the next prime number is which one? 5. So take 5. It is divisible by 5. Why? Because the last digit is 5. If the last digit is 5 or 0, then it is divisible by 5. So take 5. So 5 9s are 45, 5 1s are 55. So now you got 91. So it is not divisible by 5. So the next digit is 7. Let's check. 7 1s are 2 remaining, 7 3s are. So you got 13 is the prime number. You know 13 is a prime number. So there is no common factor or it is not divisible by any number. So you can take 13 is it as it is. So you got last digit is 1. So now write the composite number as the product of prime factorization. Which is the number we took? We took 32,760. So this can be written as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. So you got the value 2 into 2 into 2 into 3 into 3, 5 into 7 into 13. So write that one. So here 2 repeats 3 times, 3 repeats 2 times. So you can also write 2 repeats how many times? 3 times. So 2 to the power 3 into 3 repeat 2 times. So 3 to the power 2 into 5 is 1 time. Write as it 5 into 7 into 13. So this is the what? Prime factorization of the composite number. Theorem 1.3. Let P be a prime if P divides A square, then P divides A, where A is a positive integer. So I had done one small note which will easily remember for your examination, the proof of this theorem. So given P divides A square, right? So you know P be a prime. What is P? Prime means what? It has only 2 factors. Last time we discussed what is prime. If P divides A square, so what is A here? A is a positive integer. Positive integer means 0, minus 1, minus there is negative numbers as well as 0 plus positive numbers. So what is A? Positive integer. A is positive integer means plus 1, plus 2, plus 3, plus 4 and so on, any positive integer. So now here given is what? P be a prime and given P divides A square. See here I used this symbol to indicate divide. So this means P divides A square. So now we have to prove So then after that they given then, that means then after the statement after then is to prove for us. So P divides A, so that written it as P divides A. So I use this symbol to tell divide. So take this given equation as 1. P divides A square, take it as 1. Now proof. So before that I will take one example so you can understand easily. So let's take there is a P, right? So take P is equal to any prime number. So let us take 5. So P is 5 because 5 is prime number. And what is you have to take A is a positive integer, so it may be any composite or prime, any number. So let us take 30, so which is composite number, it is a positive integer, right? Next they given P divides A square, so we have to take A square is equal to what? 30 into 30, so that is 900. So this much we have. Now here say A is equal to P1 into P2 into P. How this comes? So let's just discuss by using example. See here, this is P divides A square given, means we have 5, P means 5, 5 divides A square is, this is what given, right? This is given in statement. P divides A square means we take P as 5 and A square is 900. Now we have to prove P divides A. P is what? 5 divides A means what? 30. So this is what we have to prove. This is to prove. Okay, this is what we have to prove. 5 divides 30. 5 divides 900 is given. So we have to prove 5 divides 30. Okay. Now here if you what they written, A is equal to P1 into P into P2 into P, so on into Pn. This is what? This is by fundamental theorem of arithmetic. I told in the fundamental theorem of arithmetic, that is very important, that will using in the theorem, other theorem or any problem. So this is used in theorem 1.3. Fundamental theorem of arithmetic tells us that it is any composite number can be written as product of prime number. So here A is a composite number and this P1 P2 are product of prime numbers. So here what is A? 30. So you can write 30 as a product of prime number. To write product of prime number, we have to seek prime factorization of 30. So what is the prime factorization of 30? 30 is divisible by 2. So we have to set in a standard form, that is in ascending order. First you should take least number 2. 2 ones are 2 15s are. Then 2 it is not 15 is not divisible by 2, take 3. So 3 5s are 15. Then it is divisible by 5. 5 ones are. So 30 can be written as 2 into 3 into 5. So 2 into, you can write 30 as 2 into 3 into 5. See here, this is A and these all are what? Prime numbers. So this is by fundamental theorem of arithmetic you written this as P1 into P2 into and so on into Pn. Sometimes it may be other, if for other number it may becomes more than these numbers also. So you don't know what is A. So write A is equal to P1 P2 and so on Pn, where P1 P2 Pn are prime numbers. You understood? This is from where? From fundamental theorem of arithmetic. So take this is equation 2. You have to write this is from fundamental theorem of arithmetic. Take equation 2. While squaring on both sides, equation 2 is there, no? When you square on the both sides, you get this as A square equal to P1 square into P2 square into and so on Pn square. All each term becomes square, right? So when squaring on both sides. Okay, now from, okay, take this as after squaring equation 2, you get equation 3. Then see here, given that P divides A square. So from 1, we have P divide A square. This is given in your statement. This implies, see here, instead of A square, you can write this one, P1 square into P2 square into Pn square. Why? Because A square equal to P1 square into P2 square into Pn square, right? So you can write P divides this one. What? P divides, instead of a square substitute p1 square, p2 square into pn square into p2 square into and so on pn square. Means here we written, see here we have what? P divides, means what they done? P divides a square, instead of that they written P divides p1 square, p2 square into pn square, correct? So given what we have given here, yeah, 5 divides 900. So instead of a square, what we write 5 divides what we got, p1 as the 2 square into 3 square into 5 square. Instead of 900 we write 2 square, 3 square and 5 square. This is what in the next step. So here you can see this 5 is repeated here, correct? So you know, if prime number divides any other prime number, you know that prime number have only two factors, that is only one and its number itself. So there must be number itself, there is a number which prime number divides. So here you can see 5, so here you can also see 5. So this says that p divides p1 square into p2 square into till pn square. This means there is this p is also exist in here in this any prime number. There is p, this same p in any prime number. So you can write p must be one of p1 into p2 into pn. So you have to write p is a what? P must be one of in this p1, p2, pn, any one of this, it may be p. So p divides, this means what? P divides p1 into p2 into pn. That implies, so you know from what is p1, p2, p into pn, that is a, from 2. So from 2, now substitute the value of 2, you get p1 into p2 into pn is a. So p divides a. So this is the proof. Theorem 1.4, root 2 is irrational. Now we have to prove root 2 is irrational. So how to prove root 2 is irrational? So let us prove this by contradiction. So what is contradiction? We have to take the statement in opposite form. So what is opposite form of this statement? Root 2 is irrational. So opposite of this is root 2 is rational. So this, if you prove this by taking opposite, so that is what we call contradiction proof. So now proof is what? We have to take root 2 is, this is just assumption. So let us assume root 2 is rational. So you know what is rational number? Rational numbers are in the form of what? P by Q, correct? Rational numbers are in the form of P by Q, like 3 by 2, 7 by 5, 8 by 7. So you can't further divide this, right? 3 by 2, you can't further divide this. 7 by 5, you can't further divide. So this will stop here itself. 8 by 7, you can't further divide. For example, 8 by 2, this can be further divided. 2 ones are 2 fours are. So these type of number you have to take. So these type of numbers are called co-prime. Co-prime means you can't further divide or it has no common factor. So in 8 by 2, it has a common factor. 8 has 2 fours are 8. 2 can be written as 2 ones are 2. So this has a common factor. Both has common factor 2. If you consider this number 3 by 2, you can write 3 as 3 into 1 and this can be written as 2 into 1. This can be written as 7 ones are 5 ones are. So here you can't see any common numbers, right? So these type of numbers are called what? Co-prime. So here root 2 is rational. So you can write root 2 equal to a by b. Why you can write this as a by b? Because this is root 2 is rational. Rational numbers are written in the form of p by q. Instead of p by q, we take ab. What is a and b? Let a and b are co-prime. Co-prime means there is no common factor between A and B. Okay. So we took like this. Now bring this A to left hand side. So you can write B into root 2 or anyway root 2 into B equal to A. You can write root 2 into B equal to A. Now squaring on both sides. What do you get? You get root 2 whole square into B square equal to A square. So this square cancels. So you get 2B square equal to A square. Isn't it? 2B square equal to A square. So this implies what? 2 divides A square. This implies 2 divides A square, because A square is equal to, it is a multiple of 2B square. So 8 divides 2, right? So 2 divides A square. So now see here, this is very important case here. You already learned theorem 1.3. What 1.3 tells? P is a prime. So if P divides A square, then P divides A, correct? So if this is P divides A square, then P divides A. What is P? 2, right? So 2 divides, then this implies 2 divides what? A, correct? This implies P divides A square, then P divides A. So this is from where? From theorem 1.3. Okay, now take this as equation 1. Now again, see here, this is 2 divides A square, this is equal to 2 divides A. So this implies 2 divides A. So for example, if you take 2 divides 8, so you can write 8 as a multiple of 2, right? If 2 divides 8, then 8 can be written as a multiple of 2. So 2 how much are? 2 4s are 8. Similarly, if you take 3 divides 15, this means 15 can be written as a multiple of 3. 3 how much are 15? 3 5s are 15. So you can write like this, multiple of that which number it is divisible. So you can write the multiple of that number. Similarly here, now we take 2 divides 8, means 8 equal to 2 into 4 you can write. Similarly here you have 2 divides A. So this means you can write A is equal to 2 into any number, right? So you don't know, this is the given is A. So you don't know what is the number. So let us take C. What is C? Some integer. Okay. C is some integer. Similarly, so now here we have A is equal to 2C. Isn't it? So here squaring on both sides, you get A square equal to 2C whole square. This is equal to what? A square equal to 2 square means 4C square. Now see here, you got A square equal to 4C square. Now say this equation from 1 we have A square equal to 2B square. So we know that A square equal to B square. Substitute there in value of A square is what? We have 2B square equal to 4C square. Now divide this. So 2 1s are 2 2s are. So you get B square equal to 2C square. Okay, now say this is what? B square is a multiple of 2C. B square is a multiple of 2, correct? So if it is multiple of 2, then that implies 2 divides B square. Yes, now by theorem 1.3, what we done here, right? Say similarly we have do the same process here. By using theorem 1.3, we have, what is theorem 1.3? P is a positive integer, P is a prime, and where if P divides A square, then P divides A. So same procedure here. If 2 divides B square, then that implies, then what happens? 2 divides, this implies 2 divides b square, then 2 divides b. This is from which? From theorem 1.3. Okay, so you get this one. Now take this as equation 2. Okay. Now from 1 we have 2 by a, that implies what? 2 by a square imply 2 divides a square, then that implies 2 divides a. From 1 from 1 and 2 we have what? We have 2 divides a and 2 divides b, right? From 1 and from 2. So we return, if a 2 divides a and 2 divides b, you can write a as a multiple of 2. So how you can write 2 into any number? We take c, right? Here we took c. Similarly, b also can be written as multiple of 2. Let us take simply any number like d. Okay. So here you can see 2 is the common number in both, right? 2 is the common factor between a and b. So if there is a common factor, then it is not co-prime. You know what is co-prime? Co-prime means what? There is no common factor between two numbers. But here you can see two common factor. Therefore what? What you get? A and B are not co-prime. A and B are not co-prime. So if you see here, A and B are not co-prime. But what is our assumption? A and B is co-prime because it is a rational number. We considered A and B are co-prime. Therefore, our assumption is wrong, right? Our assumption is A and B co-prime. Why? Because the root is rational. So our assumption is A and B are co-prime. But we got at last A and B are not co-prime. Therefore, our assumption is wrong. What is our assumption? Our assumption is that root 2 is rational. So this is wrong. So therefore what? Root 2 is irrational. So correct, our assumption is wrong. So what is the correct statement? Root 2 is irrational is the correct statement. So this is the proof. Now theorem 1.5. Let x be a rational number. So you know what is rational number? Rational numbers are in the form of p by q, where p and q are co-prime. Means there is a, for example, if you consider 3 by 8, there is no common factor between 3 and 8. Means you can't further divide this 3 and 8, correct? So if you consider 2 and 8, you can further divide. 2 ones are 2 fours are. So this is not this type of number it is. So what is? Let x be a rational number whose decimal expansion terminates. Then x can be terminates means what? There is a end after decimal expansion. For example, 0.135. So this is terminating. Non-terminating means what? 0.13567 goes on. There is no end. So terminate means end. It has end. So this one is which type of rational number? Terminating rational number. Means you get terminate means the remainder, when you divide you get the remainder 0. That is also called as terminate. Then x can be expressed in the form p by q. Then x can be, you know that. Why? Because x is a rational number. So that is represented in the form of p by q. P and q are what? Co-prime. It is co-prime. Co-prime means there is no common factor. Okay, this we discussed. And prime factorization of q. So what is q? P by q. In the denominator's prime factorization, you know how to see prime factorization. If you written 3 by 8, prime factorization of 8. Okay, so denominator's prime factorization is in the form of 2 to the power n and 5 to the power m. See, prime factorization of q is how it is? 2 to the power m and 5 to the power m. Means the prime which are the prime numbers? We have 2, 3, 5, 7, 11. These are our prime numbers. But in this case, in which case, if the rational number terminates and that p and q are co-prime, in that case what happens? It will only come 2 and 5, means there is only prime factorization in the form of 2 and 5. Other than that will not come when if the rational number is a terminates. So remember, only this is very simple theorem. Just if rational number terminates, if its decimal expansion terminates, then its prime factorization is always in the form of 2 or 5 or maybe 2 into 5 like that, but never it comes 3, 7, 11, it will not come. So here n and m is what? Yeah, they given n and m are non-negative integers. So you know what is integer? Integers means which one? 0, minus 1, minus 2, minus 3, plus 1, plus 2, plus 3. Non-negative integer means what? There is no negative number. So negative numbers are not there. Then which are the numbers? What is n and m? Then 0, 1, 2, 3 and so on are the n and m. Okay, which means which is also called as whole number, right? Okay, now take one example and again discuss this. Let's take 3 by 8. So here you can see 3 and 8 is a rational number. Yes, it is rational number, and this is co-prime. Yes, two numbers co-prime because 3 and 8 has no common factor between them, and they also given it terminates, and we have to prove this the denominators or q's what prime factorization is in the form of 2 or 5 or 2 into 5. So here what is 3? 3 is p. Why p? This is q. Why? Because this is 3 by 8 is a rational number which is written in the p by q form. So p is equal to 3, q is equal to 8. So totally we call this as x. 3 by 8 is called as x, right? Let x be a rational number. This whole term 3 by 8 is a x, and here 3 is p and 8 is q. Okay, where 3 and 8 or p and q are co-prime. So now we have to test the decimal expansion terminates. So whether this is example of decimal expansion terminates, let's see. So divide this. So here you write 8 and 3. So 0 point take here 0, 24, 8 3s are 24. What is the remainder? 6 is the remainder. 8 7s are 56. So 4 is the remainder. So 8 5s are 40. So you got remainder 0. So this is what? Terminating, correct? It has end. So it doesn't continue. So if you got remainder 0 and it ends, then this is what? Terminating. So therefore 3 by 8 is what? We check that it is terminating. So write, if you want you can write here. So this is what? Terminating, correct? Now we have to check the prime factorization of q. So what is q here? Oh, so we have q is equal to 8. Now see how to see prime factorization. So 8 prime factorization start from 2 prime number. So 2 4s are 8. So 2 2s are 4. 2 1s are 2. So what? How you can write? Q is equal to 8. That can be written as 2 into 2 into 2, correct? So that is, I told in the last last theorem, in arithmetic fundamental theorem of arithmetic, I told you can write if there is 2 as 2 to the power 3. Why? Because there is 3 times repeated 2, right? So q equal to 2 cube you can write. So this is what? Terminating. You get q is equal to prime factorization of q is 2 cube, which is in the form of 2, right? It may be 2 or it may be 5 or it may becomes both 2 or 5. It comes both, but never comes 3, 7, and these prime numbers will not come. Okay, now you understood what? Okay, take another example. Let's take another example. 13 by 125. Similarly here 13 is p, 125 is q. So p by q now we written. So overall this number 13 by 125 totally we call x, and you know that 13 and 125 is co-prime. Okay, all the condition holds. Now we have to check decimal expansion. 125, 13. So take 0, 0 point, 125 ones are. So what is the remainder here? 5 is the remainder. So you have to take 0 here. So 500, 125, how much are 500? 4 is 500. So you got again the remainder is 0. So therefore it is a terminating, this rational number is has a decimal expansion terminates, right? Its decimal expansion terminates. Okay. Now we know this condition holds PQ or co-prime. Okay. Now this terminates. Now we have to check the prime factorization of Q. So what is the prime factor? What is Q here? Q is equal to 125. Let's see prime factorization of 125. So it is divisible by, yes, I have to take 5. So 5, how much? 5 2s are 10. So 2 remaining, 5 5s are. Again you take 5, 5 5s are 125. 5 1s are 5. Now you can see here Q can be written as that 125 can be written as 5 into 5 into 5. So that is 5 to the power 3 because it repeated 3 times. So here you can see that this is a rational number which terminates its decimal expansion. On that time the prime factorization of Q you got again 5 to the power 3 which is in 2 or 5, right? So these are the two examples we take which a rational number terminate and P and Q are co-prime, all the condition hold, and this we check for prime factorization for Q you got in 2 and 5. There is no 3 or 7 and 11 you not got, right? So this is the theorem 1.5. Theorem 1.5. Let x is equal to p by q be a rational number. Yes, you know that rational number is written in the form of p by q. So x is a rational number. It is in the form of p by q. Okay. Such that prime factorization of q means for in the last case we take the prime factorization of q is of the form 2 to the power n into 5 to the power m. See, this theorem is similar to 1.4. This is same theorem, statement is same, but this is they given in the last set, but here this given in first set, and they given last they given x as a decimal expansion terminates, same, okay, but they given vice versa. So here this is also n and m are non-negative integer. Non-negative integer means 0, 1, 2, 3 and so on. So in that case what we done in theorem 1.4, what we done, sorry, theorem 1.5, this is 1.6, okay. So last we learnt 1.5, so this is similar to 1.5 theorem, and 1.6 is this one, okay. Now in theorem 1.5 what we did, first we take one example. For example, we take 3 by 8 and we check for whether it is terminating or non-terminating. Then it is if it terminates, then we have to prove it as Q's prime factorization in the form of 2 or 5, or it may be 2 into 5, it is in the form of this. But here what we have to do, we have to take rational number which both are co-primes. In first we have to check the prime factorization of 8. Prime factorization should be in the form of 2 or 5, that may be this is in 2 or 5, and then we have to prove this 3 by 8 is a what terminate. So this is the last step, okay, that much only. So difference is this one. So now let us take one example. So let us take 3 by 100. Okay, what we took? 3 by 100. So here first step is also, okay, what is 3 here? P, and 100 is Q. So overall we call yes, 3 and 100 are co-prime because there is no common factor. All we took the same condition. Now we have to take another condition, that is this should be in the form of 2 or 5. The prime factorization of the 100 is 2 or 5. So let's check the prime factorization of 100. So 2, take 2, 2 5s are 10, okay, 50s are 100. Again take 2, 2 25s are 100. It is not divisible by 2, so then take 5, 5 5s are, again 5 1s are. So you can write 100 is equal to 2 into 2 into 5 into 5. So see here, this holds, right? Prime factorization is in the form of 2 to the power 2 and 5 to the power 2, correct? So this is in the form of 2 and 5. But now we have to prove that its decimal expansion is terminate. So what is the rational number we have? We have 3 by 100. So now check it, it's a decimal expansion. So divide this. So 100. 3 decimal expansion. Terminating means you get remainder 0 and there is an end for the decimal expansion. So take 0.0 and again take 0. So 300, 3 is there. So what is the remainder? 0 is the remainder and it is terminating. So now we understood what is the theorem. This totally we say that rational number where p and q are co-primes, if that terminates, then it has a its q's prime factorization is what? Q's prime factorization in the form of 2 or 5, and other than that 3, 5, 3, 7 all not come. That is we learned in 1.5 theorem. Now in 1.6, if p by q is a rational number co-prime, then it is if it is in the form of if the prime factorization of q is in the form of 2 to the power n 5 to the power m, then its decimal expansion terminates. This is a proof, vice versa. Okay. Theorem 1.7. So this is the last theorem. Let x is equal to p by q, where p and q are co-prime. Okay, we know p by it is in the form of p by q means it is a rational number. Be a rational number such that the prime factorization of q. So what is the prime factorization q? You see here, focus on this, not of the form, means on that time in 1.6, 1.5 we learn it is in the form of, right? Now here not of the form. So till now we learned if it is in the form of 2 and 5 to the power 5, then how it is terminating. Now if it is not in the, if the rational number it is not if the prime factorization of q is not in the form of 2 and 5, then it is its decimal expansion is non-terminating, repeating or recurring. So I took n is equal to 0, 1, 2, 3, which means that non-negative integer. Okay, non-terminating means what? Terminating means what? It has end. Non-terminating means it has no end. Means for example 0.1576, it goes on. Okay, and repeating means what? The number after decimal expansion it goes on repeating. It is, there is no change in number like 0.8888, this goes on. Okay, there is no other number repeating, goes on repeating. So this type of number when this happens, non-terminating and repeating, when its decimal expansion is non-terminating and repeating, if it is if the prime factorization of q is not expressed in the form of 2 and 5. Let's take one example, that is 10 by 3. So here 10 is in the form of p by q, where 10 by 3 is a rational number, it holds, and 10 by 3 is 10 and 3 are co-prime, correct? It is co-prime because there is no common factor between 10 and 3. Okay, now take 10 is equal to p and 3 equal to q. Okay, so this is what? P by, it is in the form of p by q. So whole 10 by 3 is called as x. So x is equal to p by q, where p and q are co-prime. That's a condition hold. Now we have to check q is not of the form 2 to the power n into 5 to the power m. So what? Q's prime factorization is 3, right? So 3's prime factorization is what? Prime factorization of 3 is 3 itself. So no need of taking prime factorization. But now we have to check the decimal expansion. So what is the decimal expansion? That is 3 by 10. So 3 3s are 9. So here 1 is the remainder. Again you take point and take decimal. Take 1 0. So you get 3 3s are 9. Again you get 1 remainder, and this process goes on, correct? So you get 3.333. and so on. So how is this 3.333? So this goes on non-terminating, it has no end, the value is like 3.333 and so on, it has no end. Then repeating, repeating means what? Recurring. So you can see here recurring, 3 is recurring, right? So same digit is recurring. So this, when it is, when this type of decimal expansion comes, when it is not of the form, which is not of the form, prime factorization of q is not of the form 2 or 5, then its decimal expansion is non-terminating and non-recurring. So here ends the introduction part of real number. So we completed part 1 and part 2. So this is the last theorem in the chapter real number. So next, in the next video, I will discuss all the exercise problems related to real number. Thank you.